I'm sure you've heard the news, DIY enthusiasts. Protecting your gadgets is as crucial as building them. Let's dive into something hot. Meet our latest creation, a custom casing for your thermal imaging camera. Why does it matter? Well, when you're capturing precise heat signatures, the last thing you need is your gear overheating. This casing is designed to withstand high temperatures, making sure your camera performs at its best every time. First, we'll take a look at the materials. We're talking heat-resistant, durable, and easy to work with. From the initial design to the final tweaks, every step was about keeping your camera safe and functional. Then we'll guide you through the assembly process. It's simple enough for DIY enthusiasts, but robust enough for engineers. So, whether you're in a workshop or a home garage, you've got this. Don't forget to subscribe for more tech and DIY content like this. Let's get building and give your thermal camera the protection it deserves.
First of all, install SolidWorks if you haven't already. Open it up once installed. Now, open your web browser and head to Google. Search for thermal cameras. You'll notice a variety of them, different types, shapes, and sizes. Most of them contain an array of thermal sensors that give us a matrix of temperatures. Many of these sensors are priced above 2,000 Indian rupees, but take a look at this one, the IR Thermal Camera Breakout Board. This one is ideal for our use since it has header pin connectors, and its square shape makes it super easy to design a casing for. Should take a screenshot of this. We'll need it later for documentation. Now let's explore the documentation of this sensor. This particular sensor outputs an 8 by 8 pixel array and can detect temperatures ranging from 0 degrees Celsius to 80 degrees Celsius. You'll also find user guides and data sheets for most of these sensors. They are generally quite similar, so choosing any one of them should work. Here's a project example where someone has integrated the sensor with a microcontroller. Once our casing is ready, we'll also connect our sensor to a microcontroller and place everything inside a larger enclosure. Again, take screenshots and keep them in a dedicated folder for easy access. Let's jump back to SolidWorks. Always purchase your sensors from trusted websites that provide detailed documentation. Now we've selected a sensor, say, the MLX90641IR array sensor. This is quite a similar type of thermal sensor. Head over to GrabCAD Community to find the 3D model for the sensor. While you can measure a physical sensor, it's always better to use a 3D model to get accurate dimensions. Download the step files from GrabCAD. Once you have the zip file, open it in SolidWorks. Open the step file using SolidWorks. You'll now be able to rotate, view, and analyze the sensor in 3D. Once you gather those values, go ahead and make cutouts in your sketch where the holes need to be. Use extrude cut for the holes. Create boss features, raised parts, to secure the top cover. Go to File, then New, then Part. Before designing, use a caliper or refer to the data sheet to measure the actual dimensions of the sensor. You can also use the Evaluate tab in SolidWorks and select Measure to get the precise dimensions of each part of the sensor. We'll start by sketching a rectangle, length 40 millimeters, and breadth 20 millimeters. Use the Sketch tool and Smart Dimension to set these measurements accurately. Now, give the base a thickness of 1 millimeter or 2 millimeters. Even 1 millimeter provides decent strength when 3D printed, especially with durable materials like PLA or PDG. Use the extruded cut feature to add mounting holes as per the sensor layout. Then add bosses, raised circular features, needed to support nuts or to align other components. If the sensor design had been a square one, we could have made the design plug-in type connection, but since there are 3 mounting holes, we must change our design strategy to apply nuts and bolt type of connection. This ensures the sensor stays firmly attached to the enclosure, a reliable and repeatable setup for testing and deployment. Once the top cover is finished, save it as a new SolidWorks part. Now, start a new part file again for the bottom portion. Design it similar to the top, but this time, add hook-like structures where nuts and bolts can be fitted. These hooks will help us mount the sensor securely anywhere. Make sure you extrude the cutouts properly to provide space for bolts. Oops! Don't forget to add matching hooks on the top part as well. Once you're confident that all design elements are in place, save all parts separately. We need to create space for the camera lens of the thermal sensor. For that, make a circular sketch matching the camera diameter. Use extruded cut to remove that part of the surface. This cut will allow the sensor's lens to have an unobstructed view of the environment. Don't forget about the connectors, is² C/SPI. Make side cuts or slots that allow plug-and-play access. Now comes the fun part, assembling the components. Open a new assembly in SolidWorks. Import all the parts one by one. Mate them properly, face-to-face alignment, hole-to-pin, etc. Double-check for any alignment issues or interferences. Because this is a thermal imaging sensor, any trapped heat inside the enclosure can cause inaccurate readings. Here's what you can do. Add ventilation holes in non-critical areas. Include a heatsink mount if your sensor generates noticeable heat, as some MLX sensors do. Use thermally insulating materials, or keep air gaps near heat-sensitive parts. In the sample design here, I've added ventilation slots to maintain air circulation and ensure accurate temperature readings over long periods. Let's make it more personal by adding your logo. Go to Appearances Decals. Choose a PNG file of your logo. Apply it to the selected surface. Adjust the mapping and scaling until it looks just right. Once you're happy with how everything looks, you're ready to save. To package your full assembly, go to File, Pack and Go. Save everything into a zip file for easy sharing or manufacturing. Once your 3D model is ready, go to the search bar in SolidWorks and type Section View. Use this tool to visually inspect the internal sections of the model. This helps verify that all cavities, cuts, and clearances are as expected. To prepare for 3D printing, save your model as an STL file, not just the part file. Make sure to save both the top and bottom parts of the enclosure individually. We will use Ultimaker Cura, a popular slicing software that converts 3D models into G-code, which is readable by 3D printers. To get Cura Ultimaker, download it from the official Ultimaker website. Install and create an Ultimaker account if needed. Open Cura. Import your STL files into the print bed. You can move and rotate the models as needed. Here's a tip. Place both the top and bottom parts side by side for batch printing. Use the right mouse button to rotate the 3D view of the print bed. Use scroll wheel to zoom and left button to move around. Go to the Printer Settings section and choose your 3D printer model from the list. Make sure the nozzle diameter, example 0.4 millimeters, matches your printer's hardware. There are also some key parameters to set, such as infill density. Usually, 30% is good for general strength. 50 to 100% is better if the model has mechanical parts or needs higher durability. Remember that higher infill equals more strength, but also more material and time. Enable support if your model has overhangs. Support structures help the model print layer by holding up areas with no base below. Now click on Slice to generate the G-code. Then click Preview to visualize the layer-by-layer structure. Check the support and infill placement. You may notice excess support structures inside the model in the bottom part. Solution is to rotate the model by 180 degrees to minimize the need for support. This change will use less material and save print time, produce a cleaner print. After that, save the G-code to a micro SD card by clicking on Save to Disk. Insert the card into your 3D printer. You can also monitor the print directly from your laptop by connecting it to 3D printer and using Monitor tab. With your optimized model, correct print settings, and G-code file, you're ready to begin the 3D printing process confidently.
Thanks for sticking around till the end. You've just created a fully custom casing for a thermal imaging camera sensor, ready to be 3D printed or machined. If this helped you, drop a like, leave a comment if you have questions, ring the bell icon to subscribe for more awesome builds like this one. See you in the next video?